All right, if you're studying chemistry, you know just how crucial predicting the 3D shape of a molecule is for your exams. Today, we're going to master the single most important tool for that, hybridization theory. Let's just dive right in.
So, here's the big question, the puzzle that trips up so many people. We know for a fact that carbon has electrons in differently shaped orbitals, right? You've got your s's and your p orbitals. So how on earth does it manage to form 4 perfectly identical bonds like we see in methane? This isn't a trick question. It's the exact problem that hybridization theory was created to solve.
Okay, before we jump into the different types, sp, sp2, sp3, we really need to get the fundamental why. I mean, why do atoms even bother doing this? The answer is actually pretty simple, and it's the key to everything. They do it to form stronger, more stable bonds. That lowers their overall energy. And if there's one thing to remember in chemistry, it's that nature always prefers stability.
So what is hybridization, really? Honestly, the best way to think about it is as a type of mathematical mixing. An atom takes its own different orbitals, like that round s orbital and that dumbbell-shaped p orbital, and it just blends them together. And what you get is a brand new set of totally identical, hybrid orbitals that are perfectly shaped for making strong, symmetrical bonds.
Okay, pay close attention to this slide, because this is the one rule you absolutely cannot forget for your exam. It's called the conservation of orbitals, and it's basically just a simple balancing act. The number of atomic orbitals you put in is the exact same number of hybrid orbitals you get out. So you mix one s and one p, you get 2 hybrid orbitals. You mix one s and 3 p's, you get 4. It's that easy, and it works every single time. So now that we've got that core rule down, let's actually apply it. We're going to walk through the 3 main types that you have to know, no exceptions: Sp, sp2, and sp3. If you can master these 3, you'll be able to figure out the shape of a ton of different molecules. First up is sp hybridization, and just like the name tells you, we're mixing one s orbital and one p orbital. And following our rule, 1 + 1 = 2. So we create 2 new sp hybrid orbitals. Now see that word degenerate on the energy diagram? That's a key term. It just means they both have the exact same energy level, which is kind of like an average of the original s and p orbitals.
So what do these 2 identical sp orbitals do? Well, electrons repel each other, so to get as far apart as possible, they just point in opposite directions. And this is the direct link between hybridization and shape. What you get is a linear geometry with a perfect 180-degree bond angle. For your exam, you need to lock this in your brain. Sp = linear, period.
All right, next up, sp2 hybridization. Are you seeing the pattern here? The name literally gives you the recipe. One s orbital mixes with 2 p orbitals. And according to our rule, 1 + 2 gets us 3 new identical sp2 hybrid orbitals. 3 orbitals in, 3 orbitals out. It's this consistency that makes the theory so powerful.
So how do 3 identical orbitals spread out to minimize that repulsion? Well, they form a flat triangle shape. We call this trigonoplanar geometry, and it has perfect 120-degree angles between each orbital. So here's your next big takeaway for your notes. sp2 means trigonoplanar.
And last but not least, we have sp3 hybridization, which brings us right back to that methane puzzle we started with. In this case, the carbon atom mixes its one s orbital with all 3 of its p orbitals, so 1 + 3 = 4, and it creates 4 new, perfectly identical sp3 hybrid orbitals, all ready to form some bonds.
And what shape do those 4 sp3 orbitals make? They arrange themselves in that classic 3D shape called a tetrahedron, with that famous bond angle of 109.5 degrees. And there you have it. That's the solution to our puzzle. Carbon undergoes sp3 hybridization to create 4 identical orbitals, which lets it form the 4 identical symmetrical bonds in methane. Puzzle solved. Okay, so we've pretty much mastered how hybrid orbitals form the basic framework of a molecule, the single bonds. But what about double bonds and triple bonds? To really get those, we need to introduce 2 types of covalent bonds you must know, sigma and pi. First up is the sigma bond. Think of these as the backbone, the strong foundation of every single bond. They form from a direct, head-on overlap of orbitals, right along the line connecting the 2 atoms. And here's a key fact. Every single bond you see is a sigma bond, and every double or triple bond has exactly 1 sigma bond in it. So you might be wondering, what about those p orbitals that sometimes get left out of the mixing process? They don't just vanish, they go on to form pi bonds. A pi bond is formed by a weaker, sideways overlap of these unhybridized p orbitals. And as you can see in the diagram, the electron cloud isn't directly between the atoms, it's in these two lobes, one above and one below the main sigma bond.
Okay, this slide right here is pure gold for your study notes. Seriously, you might want to grab a screenshot of this. It sums up all the critical differences. Sigma bonds, strong, head-on overlap, can use any type of orbital. Pi bonds, weaker, sideways overlap, and they only use those leftover unhybridized p orbitals. The sigma bond is always the first one there. The pi bonds are the second and third bonds that make up your double and triple bonds.
All right, let's put it all together. Let's combine sigma and pi bonds and see exactly how they build the multiple bonds we see in so many molecules.
So let's take a look at ethane, C2H4. Each carbon atom here is sp2 hybridized, which, as we know, gives it that trigonal planar shape. Now these sp2 orbitals form the sigma bond framework. That's 1 carbon-carbon sigma bond and 4 carbon-hydrogen sigma bonds. But remember, since it's sp2, each carbon has one unhybridized p orbital left over. These two p orbitals overlap sideways to form a pi bond. And there you go. A carbon-carbon double bond is simply one strong sigma bond plus one weaker pi bond.
Now let's level up to ethene, C2H2. In this molecule, each carbon is sp hybridized, which means it has a linear shape. They form a sigma bond between the two carbons. But since it's sp hybridization, each carbon has two unhybridized p orbitals left over. These then overlap to form two separate pi bonds. And this explains a triple bond perfectly. It is always one central sigma bond surrounded by two pi bonds.
And there you have it. By putting together hybridization with sigma and pi bonds, you can now predict the 3D geometry of a huge range of molecules. But this, of course, leads to an even cooler question. What happens when those pi bond electrons aren't just stuck between two atoms, but are actually free to roam across an entire molecule? Well, that's where things like resonance come into play. And that's a story for another time.